All right. So we are going to today we're going to do the notes, the states of matter and phase changes one. Okay. Um, so start with that. Okay. Now I'll tell you guys what I told the other classes. So um, I know you guys have done states of matter stuff before in like middle school and maybe even some high school class, depends on what you've taken or whatever. But like you've done states of matter before, right? So I'm going to go through this info kind of quickly, and I'm not going to read all of it because I don't want to like just sit here and bore you to death with stuff you've already known. I'm going to try to hit the highlights and then explain some of the stuff that you might not have learned before, or you might have, but it might have, just trying to kind of like shake the rust off of some stuff. But if I go too fast or if I go over something I don't explain it and you're confused, please ask, because if you're confused, that probably means other people are. Okay. So if at any point something's not making sense, just please ask me. All right. So states of matter. They've got five sort of categories. I'm guessing that you guys are somewhat familiar with four of the five at least. Probably the top four: plasma, gas, liquid, and solid. Yes. Okay. Um, One thing to note about plasma is, remember, we're talking about plasma as a state of matter, not a substance. So like there is plasma substance, like there's plasma, like there's something called plasma in your blood and stuff like that. That's not the same thing. This is plasma as a state of matter. So it's other substances in plasma form. Okay, so I don't know if anybody has like relatives or family members or whatever that like might do construction or anything. But in construction, sometimes they'll even have like the plasma torches or the plasma cutters that can help cut metal. And essentially, what happens with plasma is it's substance that get ionized, which essentially means there's a crap ton of energy that's shoved through it, and it causes it to strip electrons from it and be at a really high energy state. Is that state of matter? Okay. Um, so that's plasma. And then we have the three that you're probably familiar with: gas, liquid, and solid. Right. The only thing I want to kind of mention on these is, so they sort of categorize or tell the difference between them on two factors: volume and shape. Okay, so for example, if I have this paper clip, which is a solid, right, and I put it in my hand, it still is in that shape and it's taking up that amount of space, right? It doesn't change. And if I were to take it from my hand and I were to put it in this cup, does that change the size or the volume it's taken up? No, it stays the same, right? So if you look at solid, retains volume, retains its own shape. That means, so a solid, neither the volume nor the shape changes based on the container. Okay. What about a liquid? Volume and shape. If you move it from one container to another, does the shape change? Yes. Yeah. What about the volume, amount of space it takes up? Does that change? Shaking his no. No. So imagine we had a gallon of water, like in a plastic gallon, and you took it and you poured it into a bathtub. Okay. Is it going to still be in the shape of the gallon? No, it'd be kind of crazy. Like, it sits there like in a gallon. Like, no. It takes it fills, like, goes to the bottom of the tub or whatever. Okay, but if you pour it in there, you turn around and you turn back around, it's not like all of a sudden the bathtub's all filled up with water, right? Like, you put a gallon and you turn back and like, ooh, like, magically, that'd be kind of cool, but no. So the volume stays the same. So a, a, a liquid, the shape changes, but the volume stays the same, based, going from container to container. What do you guys think about a gas? It's going to be the volume and the shape. Are they going to stay the same? Both stay the same, both change, or one stay the same, one change? Both change. Good. Both change. You put a gas from take a gas from one container to another. Obviously, it doesn't have its own shape, right? It changes whatever the container is. What happens when you take a gas from one container to another in terms of the volume? What does it do? Anybody know? So, what's that? The amount stays the same, but the volume won't. If I okay. Well, people who are watching this on the video are going to have to kind of imagine. All right, so I have that wasn't super successful. Hold on. Oh, for the love. There we go. Okay, so we've got a decent amount of air in here, right? Okay, now, so the air in this bag is the air in the bag is filling up this volume of this bag, right? Taking up this amount of space. What happens if I take this and I take this gallon bag and I sneak the other bag inside of there, right? And then see if I can actually pull this off. Come on, sucker. I'm not going to be good enough. Oh, wait. Oh. So close.
Just pop it. Pop it.
I thought of that, but I'm worried I'm going to pop the outer one. Here, we'll do it like this. See, now we're using two brains. Two brains are better than one. Okay. So now I have the paper clip in there. Okay. So now so if I take this and I pierce the inner one, right? So no molecules are escaping, right? Like no molecules are escaping. So what happens when the gas comes out of the smaller one into this bigger thing? What does the gas do?
Fills it up.
What's that?
Fills it up.
Yeah, good. It fills it up, right? It doesn't just stay in the same amount of space that the small one was in. We say it like expands to fill the container, or if it fills container completely, it expands to fill its container. So whenever a gas goes into something, like you take a gas from one container to another, when it goes in the new container, it will expand to fill the container. Okay, now, that doesn't mean you're getting more molecules. Just remember, like gas molecules are moving really fast and they're spread apart. So it just means they kind of like spread throughout the thing. So imagine you take like a class of like second graders, right? From they're in their classroom, and then they're moving around doing whatever, and then you take them to a gym. So in the gym, they're going to run around like crazy all over the place, and they're just going to kind of fill the whole gym up. But it's not like there's more of them. They just go throughout the whole thing. Does that make sense? Okay. All right. So that's the difference between these. Gas, both volume and shape change. A liquid, the shape changes, the volume doesn't. Solid, neither, both the shape and the volume stay the same from container to container, okay? All right. Any questions on any of that stuff? I'm not going to read all the rest. You can look at the rest of it. You've probably seen a lot of that before. The fifth one, Bose-Einstein condensate. Okay. Is the fifth state of matter. You might not be as familiar with it. Now, first hour, I did a whole explanation of absolute zero and spent like 10 minutes on it before somebody spoke up and said that we've talked about it a little bit before. I'm like, oh, great. So we've talked about absolute zero a little bit before this year, right?
Yeah.
Does anybody remember anything about it? What absolute zero is, or kind of like the idea behind it or anything?
Lowest possible temperature.
Good, because yes, lowest possible temperature you can go. Which means what would be true about the energy that the substance had if it was at absolute zero? How much energy would it have? Go.
Not a lot.
Not a lot. More specifically,
Plus zero.
zero. Yeah, not at all. Good. It would have no energy. So just to kind of like I said, we've gone over this, just kind of shake some rust off and kind of understand the concept. What is heat in general? Heat is a form of what? Yeah, form of energy, right? Good. What causes heat in like a sub? Like what is it that makes the heat, or what gives heat energy? Friction between what? Yeah, molecules. Good. So molecules move around, and the friction between the molecules is what creates heat. So really, heat comes from the movement of the molecules, right? And heat's energy. Movement is also a form of energy, kinetic, right? So if you take all the energy out of something, all of it, has zero energy, that means there's no heat, there's no energy, so there's no heat, no movement, nothing at absolute zero. Okay. Make sense? So coldest possible temp. For a Bose-Einstein condensate, all I really want you guys to remember, what I really want you guys to remember for the Bose-Einstein condensate is that the Bose-Einstein condensate state of matter occurs at really low temperatures close to absolute zero. Okay, that's why I highlighted it. Okay, questions? All right, let's flip. Okay, so I highlighted, oh yeah.
When you pull like an object off
Mm-hmm.
to extent, won't it get smaller?
Okay. Hold on to that question for a sec. That actually we'll kind of talk about that with what we're going here. Okay. So state of matter changes. Again, I know you guys have done some of this. I just want to sort of frame the way you think about this, so we don't make mistakes about identifying stuff. Okay. So remember, phase changes, state of matter changes are not chemical changes. They're just physical changes. All that is happening is the molecules, that was close. The molecules are either moving faster and getting further apart, or they're moving slower and getting closer together. But it's the same substance. All right? So we have 6 state of matter changes. We've categorized them by what's happening to the energy. Now, before we talk about that, I want to talk about hot and cold a little bit. We commonly think of things as hot and cold, but hot and cold are, they're like subjective. It's like comparative terms. So the example I've been using kind of is like, I'm assuming at some point you guys have all, is that you've been outside when it's really, really cold, you come in, your hands are really cold. If you put them under water, even if the water is like just normal room temp, or even kind of cold, it feels pretty hot, right? Because your hands are so cold. All right. So we wouldn't really think of the water as hot, but it feels hot because we're comparing it to our hands that are really super cold. So hot and cold are comparative. So they're not really great things to think about the phase changes with. So for example, what you want to do is you want to think about these in terms of what state of matter is it coming from and what state of matter is it going to and what's happening to the energy. All right. So, for example, freezing or fusion, okay, like water turning to ice, right? Now, okay, we've got two categories of energy. There's exothermic and endothermic. Thermic refers to energy or kind of like heat. You've heard of the term thermal, right? Like thermal underwear or stuff like that. That's like talks about like keeping heat and stuff. Okay, thermal is referring to heat or energy. You've got exothermic and endothermic. Here's how I remember them, and hopefully this will help you. Exo is like exit. Exit. So if something is exothermic, energy is leaving the substance, exiting. Endo is like enter. So if something is endothermic, energy is entering into it. Right? Now, is everybody good on that? Okay. Now, here's where it can be a little harder. You got to kind of think of what's happening to remember which one it is. So think about water turning into ice. If you're talking about water turning into ice, how do we make that happen? Like what do we do to water to turn into ice? Yeah, dude.
Get it really cold.
Get it really cold, right? You get it really cold. Okay. So we get it really cold. A lot of times people think like, oh, okay, you're getting it cold, so like if something is exothermic, it's giving off heat, so it's gonna be hot. Like if you're burning a piece of wood, that's an exothermic reaction, right? It's giving off heat. Okay, but what you have to remember is, again, not about hot or cold. It's about, are we taking away energy or are we adding energy? So we make it really cold. What do we do to make water colder in terms of the energy? Good.
Take it away.
Bingo. Taking it away. So that would actually be exothermic, right? Because energy is leaving the water. We're good? Make sense? So you have to think about it in terms of, is the energy leaving or going into the substance? All right? And again, don't think of it as hot or cold. A good example of that is you burn a candle. So when you burn a candle, actually two things are happening. You have some chemical reaction where the wax is actually burning. That's why candles get shorter over time. But you also have some where you're just melting the wax, right? Okay, so you're burning a candle for a while, you blow it out. What happens to the wax? Hardens, right? What's that called? Which phase change is that? It's an exothermic, correct. Which one of the three?
Freezing, fusion.
Yeah, freezing fusion. It's freezing. It seems weird, right? Because like it's not cold, like it's wax. It's it's hot and it's kind of room temp. So that throws people off because people always think of freezing as cold. So you got to be really careful. Think of freezing not as being cold, but freezing is turning from a solid or from a liquid to a solid. All right. Have you guys ever seen like pictures or anything of like the big huge like industrial things where they melt down those the big pots of metal, like molten metal, and then they like pour it into a mold and let it cool and harden? Okay, that's super, super hot. But technically that process, because it's going from a liquid metal to a solid, that's technically freezing. Because it's going from a liquid to a solid. And energy is leaving it. All right? So we're good on that? All right, there's three of them. Freezing and condensation, you're probably a little more familiar with. Deposition. Deposition is turning from a gas to a solid without going to a liquid in between. Goes directly from a gas to a solid. So the example I have there is frost. My question to you guys is, how do we know that when frost, like in the winter, you go out and you like see on your car windshield or on the ground or whatever, it's frost, right? How do you know from observation, how do you know that it went directly from water vapor in the air to the solid frost on the surface of the ground or the windshield or whatever? How do you know it didn't go to a liquid first? What does it look like? What? Ice? Frost looks like ice? Yeah, sort of. But what, like, if you had to just, okay, so let me ask you this. So we call it ice when we turn liquid into solid, right? If you guys had to describe the difference, what you observed, the difference between frost and ice, what would you describe the difference? Okay, ice can like it can be thicker.
Ice can be clear.
Yeah, like more clear, right? Frost is like kind of like foggy whitish usually, right? And if you look at it closely, a lot of times they'll have like little like there'll be like crystals, like crystal shapes and stuff in it. Whereas ice is typically kind of like all one or smooth and kind of clearish, right? Okay, so if you think about that, that's actually the clue or the observation that tells you that it didn't do that. Because if it went from a gas to a liquid and then to a solid and froze, it would look more like ice and less like frost. Like every once in a while we'll get like we call them ice storms, but it's basically where it like rains or whatever, and then it freezes when it hits the ground or hits stuff, and like the trees have like it looks like they've been encased in ice and everything all over. That is what it looks like when water vapor goes from a gas to a liquid to a solid. It looks a lot different than frost. So frost is literally the water vapor in the air going directly to a solid on the surface without turning to a liquid in between. Okay? It's called deposition. Think of like depositing, like putting something on. It's like taking the vapor out of the air and putting it into a solid. Okay. All right. Questions on those? Okay. Endothermic means the thing is gaining energy, right? Absorbing energy, taking it in. Again, don't think of it as hot or cold. Here's an example. You know those what are they called? Oh my gosh, like the ice pack that you like burst the inside when you like heat up or whatever. Like the chemical reaction. It feels when you put it, it feels cold, right? Why does it feel cold? Well, I mean, to do its job, but what's going on in like
Oh,
it's losing heat?
it's taking the heat from the air.
Yeah, well, and from you, right? So the reason it feels cold is because the ice pack is absorbing energy away from you. So it's making you feel colder because it's taking energy away from you. But the ice pack itself is actually gaining energy. So that actually it feels cold to us, but that actually would be endothermic. It's gaining energy. And if you think about it, it makes sense because what happens over time to them? Yeah, they warm up, right? Like it's not cool anymore after a while because it gains energy. Okay. All right, good. So melting and vaporization, you guys should be pretty decent with. Vaporization we can break into two things though. Vaporization is the change from a liquid to a gas, generically. There's sort of two categories. There's evaporation and boiling. Okay. So you all get treated to my wonderful drawing skills today. I don't want you to be jealous. It's taken years for me to get this good. All right. So imagine like a pet water bowl. I said food bowl. That doesn't make sense to be food bowl, water bowl. A water and a pet food bowl, whatever. Okay. So imagine water molecules. Okay. I'm not going to fill this all in. I'm just going to do a couple of layers. Okay. I'm not filling it all. But so you've got water and like the water molecules and whatever, right? Okay. Evaporation occurs at the surface. Anybody know what happens with evaporation? I mean, I know that you know what happens, but like how it happens or what's going on at the molecular level?
They get separated so fire just floats away.
Yeah, good. Okay. So what happens is some of these, see if I can pull this off here. Some of these at the surface get separated and move far enough away to be gases. Now, here's the real kicker. Anybody know how that happens? Or why? Either way, I guess. Either way you could say it. I'm out of here. Okay, so let me ask you guys this. In order for something to turn from a liquid to a gas, what do we know has to happen?
It has to go on.
Good, gain energy somehow, right? Has to gain energy. So then logically what would make sense is somehow the molecules on the surface have to gain energy. Any idea how that happens?
Is it friction again?
They have friction, but the friction between the water molecules is not going to increase by itself. It won't just increase. Let me ask you this. Anybody know how you can make something evaporate faster? Oh, actually, no. That would slow it down, putting a lid on it. What's that? I'm sorry. Okay, so one way could be heated up. You could heat it up more, but not get it to boiling. Why would that make it evaporate faster? Yeah, you're adding energy, right? So like you're adding energy, it's going to move faster, so it's going to evaporate a little more quickly because it'll be easier for the molecules to go away. What if you don't change the temperature, the heat of it? What's a way you can make something evaporate faster?
More of it?
No? What does sweat do for us? How does it cool us down? Well, I guess it's kind of not a bad example, it's a good example, but it uses temperature. So sweat cools us down by absorbing heat from our body, and then it uses that heat to turn from a liquid to a gas. Okay, so that's more of the heat example. Now, if you've been, so like you probably all done this, like been working out or playing sports or something like that, and you worked up a sweat. What can what sort of action can occur to you that will make the evaporation happen faster, and it'll make it feel colder, like the sweat and everything like that, because it's evaporating faster? You walk in front of a fan, right? Have you ever done that, or walked in something like, if you're sweating or outside and then like a breeze picks up, it feels cooler, right? Anybody know? Well, so the reason it feels cooler is because the evaporation is happening faster. Anybody know why it's happening faster?
Give it a more of a chance to fly away.
Sort of. So in the water bowl thingy, what's above the water? Gases, air, right? There's air molecules. Air molecules are like the psychotic little toddlers of the molecule world, right? They're moving around super fast, no pattern, no rhyme, no reason. They're just shooting all over the place, right? And every once in a while they run into each other. Okay, now but they're moving all over the place, right? So air molecules are constantly colliding with each other. They're constantly colliding with the walls of the container or,
with the water.
yeah, the surface of the water, right? So the way evaporation works is air molecules are constantly striking the surface. There's where your energy comes from. Every once in a while, you'll get enough air molecules or enough energy, and it'll pop a water molecule off the surface and send it into the air, turning it into a gas. So slowly over time, as air molecules continue to hit the surface, they just keep popping off water molecules. That's how evaporation works. Does that make sense? Does it make sense why it happens at the surface too? Because that's where the air molecules are striking, right? Okay, good. Now, let's talk about the second thing. Boiling, which you guys are probably a little more familiar with. All right, so boiling occurs, like it says in here, boiling occurs below the surface. Sorry, there we go. Below the surface at the temperature of the vaporization point, or what we normally call the boiling point, right? So again, I'm not gonna. Okay, so you got water molecules. Typically, what do we do to make something boil? Yeah, heat it up, right? Add fire. Okay. So we had fire. So say, I'm assuming you've all at some point, boiled yourself or seen, parents boil water, something like that in like a pot or whatever. What do you see in the boiling pot of water that tells you it's getting close to what we consider boiling, like the rolling bubbles, right? Yeah. Where are the bubbles? Yeah, yes, good. It starts forming bubbles, right? Like on the usually like on the bottom and on the edges and stuff like that. Right? Now, here's the double jeopardy question. What are those bubbles made of? Nope. Ooh, nope. Nope. Nope.
Can we get a hint?
Okay, so here's the hint.
Water.
What?
I said water.
Bingo.
Oh.
Those are water in gas form. Just water. They're literally gas bubbles of water as a gas, water vapor. They're water vapor bubbles. Okay, now if you think about it, it actually starts to make sense because think about where they're forming. Underneath it, like all that's in the pot is water, right? And they're forming like at the bottom along the edge or whatever, because that's where the heat's being applied. So what's happening is the heat's being applied here. The water molecules at the bottom where the heat's hitting, they're absorbing it and absorbing it. What does absorbing heat or energy cause them to do? Move around faster, right? And as they move around faster, what starts to happen? They absorb more, they move around faster, and they start to spread apart, right? So they're getting more and more worked up, they're getting more and more energy, and eventually the molecules at the bottom they get far enough apart that they turn into a gas. That's the bubbles. Just water as a gas.